The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples.
In the 1920s, astronomers made a startling discovery when observing galaxies beyond our own. These galaxies, once thought to be nebulas within the Milky Way, were receding from us. This observation led to the realization that the universe is in a state of expansion. It also led to the Big Bang theory, the most widely accepted cosmological model for how the universe came to be. By the 1990s, the Hubble Space Telescope gave astronomers the opportunity to make the deepest views of the universe ever. While it was hoped that Hubble's observations would resolve some of the greatest questions in cosmology and astronomy, these observations only deepened the mystery, as they indicated that the rate of expansion, otherwise known as the Hubble Constant, was accelerating with time. This led to the popular notion that a mysterious force was behind cosmic expansion, which came to be known as dark energy. However, this was not the only cosmological mystery that Hubble would deepen. In addition, its observations at galaxies that existed during the early universe did not agree with local distance measurements. The same discrepancy was noticed when the European Space Agency's Planck mission mapped out the cosmic microwave background. In short, distance measurements and what they said about the rate at which the universe is expanding differed depending on the method used and where we looked. Looking locally produced one set of estimates. Looking back to the farthest reaches of space and time produced another. This came to be known as the Hubble Tension, or the crisis in cosmology. And according to the latest observations from the James Webb Space Telescope, this crisis is far from resolved. As we covered in previous episodes dedicated to Einstein's revolution and the history of cosmology, by the early 20th century, scientists had made a number of very profound cosmological discoveries. The first was the realization that what appeared to be clouds of nebulous gases, which astronomers assumed were orbiting within the Milky Way, were in fact distant galaxies. This was due to improved instruments that could finally resolve individual stars in these galaxies. Not long thereafter, between 1905 and 1916, Einstein proposed his revolutionary theory of relativity. This theory was described in several seminal papers released in 1905, which described how light behaved in a vacuum and how speed affects the observer's perception of time, space, and mass. This came to be known as Einstein's theory of special relativity. Between 1905 and 1916, Einstein expanded the theory to account for gravity. The end result was his general theory of relativity, which describes how mass and gravity are related and how these alter the curvature of space-time. Once this theory was experimentally verified only 3 years later, with the Eddington experiment, scientists began exploring potential resolutions to Einstein's field equations. Like Einstein, many scientists were concerned that, if correct, his theory predicted that the universe would be in a state of contraction, eventually being swallowed up in a big crunch. To resolve this, Einstein added a parameter to his field equations, which he called the cosmological constant, a mysterious yet unknown force that held back gravity and kept the universe in a static, stable form. However, several physicists noted that depending upon the value of this parameter, the universe could also be in a state of expansion. This explanation was used to explain observations made by many astronomers who noted that galaxies beyond the Milky Way appeared to be receding from us. Essentially, when astronomers looked at the majority of these galaxies beyond our own, they noted that the light appeared to be undergoing a Doppler shift, where the wavelength was shifted towards the red end of the spectrum. A possible explanation for this was that the space between our galaxy and those being observed was expanding. As light traveled through this expanding medium, the wavelength of the light would be lengthened, causing it to appear more reddish.
A similar phenomenon was happening with the galaxies located closest to us, such as Andromeda and the Triangulum galaxy. As opposed to redshift, these galaxies exhibited signs of blue shift, where the wavelength of light coming from them was shifted towards the blue end of the spectrum because the space between them and our galaxy was being compressed. By 1927 and 1929, Belgian priest and astronomer Georges Lemaitre and American astronomer Edwin Hubble independently concluded that the rate at which the universe was expanding could be calculated. This came to be known as Hubble's law, or the Hubble-Lemaitre law, in recognition of both astronomers independently deriving it, while the rate at which the cosmos was expanding came to be known as the Hubble Constant, or Hubble-Lemaitre constant.
The Hubble Space Telescope, which launched in 1990, was so named because one of the main things that it would be investigating was the Hubble-Lemaitre constant. In many respects, Hubble was the culmination of nearly 50 years of lobbying and research by NASA. While Hubble was not technically the first space telescope ever to be deployed, it was the first dedicated mission that was capable of conducting deep-field astronomy in the optical, near-infrared, and ultraviolet wavelengths. Operating in orbit also meant that it was not subject to atmospheric interference, which for ground-based telescopes requires adaptive optics and other methods that correct for the distortion of light. Prior to Hubble, astronomers could only see objects in our universe up to a distance of about 4 billion light-years, which effectively meant that they were confined to observing the evolution of the universe during the past 4 billion years. Hubble extended this range considerably, first to 10 billion light-years, and once it got into its ultra-deep field and extreme deep field programs, it was able to observe some of the earliest galaxies in the universe, which existed more than 13 billion years ago. As mentioned, these observations revealed that cosmic expansion was accelerating with time. Whereas the rate had been relatively consistent up until about 9 billion years after the Big Bang, within the past 4 billion years, it was speeding up. This led astronomers to reconsider Einstein's cosmological constant, a force that held back gravity, which they now reimagined as dark energy. Similar in theory to dark matter, a mysterious invisible mass that constituted most of the matter in our universe, dark energy was envisioned as a mysterious invisible force that was working against gravity. Over time, as the large-scale structures of the universe expanded farther and farther apart, the gravitational attraction between these large structures became less and less. All this led to the most widely accepted model of cosmology that astronomers have been using for decades. It is known as the lambda cold dark matter model. And whereas lambda represents the cosmological constant, aka the Hubble-Lemaitre constant, consistent with Einstein's earlier field equations, cold dark matter referred to a specific theory of dark matter in which dark matter particles are large, slow-moving, and only interact with normal or visible matter through gravity, the weakest of the 4 fundamental forces of the universe. But as also mentioned, Hubble's observations also led to problems with what is known as the cosmic distance ladder. This refers to the different methods that astronomers use for measuring cosmic distances. For local distance measurements, or objects that are within 10,000 light-years of the solar system, astronomers will rely on parallax measurements. This time-honored method relies on the principles of trigonometry and consists of measuring the angle of a star relative to Earth at different times of the year, coinciding with the Earth being in different locations around the Sun, and comparing the angular separation. The next rung in the ladder, so to speak, consists of using standard candles for distance measurement. In astronomy, this refers to monitoring stars for changes in their brightness, or what is known as a light curve. In this case, astronomers use variable stars, or stars that are known to vary in brightness over time, in particular Cepheid variables, which are known to pulsate in a way that is stable and predictable. For over a century, astronomers have understood that the pulsations and the variation of brightness in these stars can yield accurate distance measurements. And whereas ground-based telescopes were able to measure distances of up to 13 million light-years, the Hubble Space Telescope has been able to make distance measurements using Cepheid variables to distances of up to 100 million years. For the third rung in the cosmic ladder, astronomers rely on the brightest stellar objects, Type 1a supernovas, and how their brightness diminishes over time. This method allows astronomers to measure the distance to objects up to 1 billion light-years away. The fourth and final rung in the ladder consists of measuring cosmological redshift. Since the early 20th century, astronomers used redshift to measure how fast galaxies were receding from our own. In addition, since the 1960s, astronomers have been aware of the cosmic microwave background, or CMB, the remnant radiation left over after the Big Bang. This is the furthest form of light that any telescope can see, and is proof that the Big Bang model of cosmology is in fact correct. Between the 1980s and 2010, astronomers have obtained increasingly accurate measurements of the cosmic microwave background, including its polarization and redshift, thanks to missions like the Soviet Relict 1, NASA's Cosmic Background Explorer, or COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, and the European Space Agency's Planck spacecraft. By conducting redshift measurements of the CMB, as well as objects that are farthest from the Milky Way and at the very edge of detection, in other words, objects that existed during the early universe, astronomers are capable of making distance measurements of up to 13 billion light-years. This is where troubles truly began with Hubble's measurements, when observing galaxies that existed over 13 billion years ago. Only a few 100 million years after the Big Bang, Hubble noted redshift values that did not correspond to other distance measurements. The same is true of redshift measurements of the CMB. Whereas local distance measurements, using parallax and standard candles, yields a value of about 26,000 kilometers per hour per megaparsec, redshift measurements of the CMB and distant galaxies yields an entirely different value of roughly 24,000 kilometers an hour per megaparsec. In other words, the universe appears to be expanding faster in our vicinity. While it was hoped that the James Webb Space Telescope would resolve this crisis in cosmology, it too has only added to the problem. Using its more advanced optics and advanced suite of scientific instruments, the James Webb has repeated many of Hubble's observations, which recently included a deep fields look at galaxies that existed during the early universe. Unfortunately, Webb's own measurements indicated that Hubble was right on the money, and that its redshift measurements of these galaxies were in fact correct. And so the Hubble tension remains. These findings have reinvigorated alternative theories of gravity, such as modified Newtonian dynamics, or MOND. This view, which is supported by a minority of astrophysicists, essentially states that the gravitational force within galaxies varies inversely with the radius. According to one theory of modified gravity, our galaxy may be in the center of an underdensity, which would explain why our observations don't match up. While this theory does present a possible resolution to the Hubble tension, it raises other theoretical problems and discrepancies in its place. Other proposed resolutions include modified general relativity, primordial magnetic fields, or the existence of dark matter and dark energy that behave differently in the early universe. These theories can generally be divided into two categories: early-time solutions and late-time solutions. Early-time solutions offer explanations that occurred shortly after the Big Bang, while late-time solutions occurred more recently in cosmic history. Early-time solutions postulate that the energy density of the early universe was somehow increased before recombination, the cosmological epoch during which charged electrons and protons became bound to form neutral hydrogen mere seconds after the Big Bang. In a recent study, a team of astrophysicists from Johns Hopkins University and the Space Telescope Science Institute argued that a form of early dark energy existed at this time, which decayed faster than other forms of radiation after recombination occurred. Big-time solutions, on the other hand, postulate that the energy density in the post-recombination universe, roughly 300,000 years after the Big Bang, is smaller than what is predicted by the standard lambda cold dark matter model. However, none of these theories offer an immediate resolution and will need to be tested and verified based on future observations, not only by the James Webb Space Telescope, but Hubble's successor, the Nancy Grace Roman Space Telescope, as well as the European Space Agency's Euclid mission. The Euclid mission launched on July 1st, 2023, and has already began collecting its first light. The Nancy Grace Roman Space Telescope, meanwhile, is expected to launch in late 2026 or early 2027. Both of these observatories will use wide-field and wide-angle telescopes to observe how the cosmos has expanded over the course of billions of years in the hopes of confirming and measuring the influence of dark energy. Once more, scientists are forced to await future discoveries in order to resolve the current scientific problems. Now, when it comes to the Hubble tension, it is clear that this particular crisis in cosmology is destined to continue. Meanwhile, all we can do is wait and look forward to the next round of scientific results and research findings, in the hopes that someday astronomers, cosmologists, and astrophysicists will be able to say with confidence, we now know how the universe began and how it's changed over time and all the underlying physics that governs it. That day may never come. But such is the nature of cosmology. It is like an onion constantly shedding its skin, except we find ourselves on the inside of the onion, clawing our way out. With every new layer that we shed, we find that the universe that we inhabit is larger than we previously expected, and that the laws which appeared to govern things on the smaller scales don't necessarily govern things on the larger scale. But we keep looking with increasingly sophisticated instruments, hoping that someday we'll find our way to the last layer and the last great cosmological mystery. Thank you for listening. I'm Matt Williams, and this has been Stories from Space.